Hello, everybody. So this is the lecture on section 2.1 on the area between two curves. And the basic problem in this section is as follows. Consider two functions f(x) and gx satisfying f(x) is less than or equal to gx for all x in the interval from a to b. So what you have is a picture like this. So here's a and here's b, and then the function g of x is greater than that of f of x. Put the b here. On that interval. Okay, so the question now is, what is this area here? What is the area between f and g? All right. So, by the way, this is y equals fx, and this is y equals gx. When I say f is less than or equal to g, on that interval, it means that g is appearing above f. Okay, what is the area in between the curves? Okay, notice that this is inherently a positive answer. The area as defined must be positive. Okay, when we're talking about the area of a geometric object, just in the abstract like that, it's got to be a positive thing. I know when we were talking about integrals in the past, areas below the x-axis are considered to be negative areas, and areas above are considered to be positive areas. But here we're just talking about the area of this shape, which is defined as a positive thing. Okay, so your answer to such a question has always got to be positive. Now, you might have guessed correctly that the area between f and g is equal to the integral, of course the area from a to b, of the top curve gx minus the bottom curve fx dx. And you would, if you would guess that, you would be correct. Now it's not 100% obvious why that's the case. If g and f are both above the x-axis, then it is indeed the case. Okay, and obviously so, because you're taking the area underneath g and subtracting from it the area underneath f. Considering this to be a negative area, when you're subtracting it, that means you're adding it and all that stuff. And that's fine. I mean, that's correct. But what we're really going for in Chapter 2 here is a more specific understanding of what the integral is. And this is a starting point, a nice starting point. So let's analyze this problem from the standpoint of the definition of the integral. Not the fundamental theorem of calculus, the definition of the integral. Okay, so to prove this is actually the formula, calculates the area in question, let's start with the definition of the integral from a to b of fx dx. That definition is the integral from a to b of fx dx is equal to the limit as n goes to infinity, sum I equals 1 to n, that Riemann sum fxi delta x, in which delta x is b minus a over n, and xi is equal to a plus I delta x. Now, you can forget about that picture from Calc 1 of the area under the curve with those rectangles, and each rectangle has this area, and so you add up the rectangles and let the rectangles get real skinny by taking the limit as n goes to infinity, and then that equals the area that you want, right? That's the standard setup for the integral. Okay, that's standard, explanation of what this means. But here we're going for alternate explanations. Okay, there's one geometric meaning behind this. There's many geometric meanings behind this. So we're going to attach lots of different geometric meanings to this integral. So towards that end, the definition of the integral is just this, devoid of any inherent geometric meaning. Okay, so now let's apply this definition to this area in question that we're trying to calculate. Okay, we're going to apply it in a familiar way, but later on it'll be less familiar. Okay, so let's grab this picture here, and let's take a look at it down here. Okay, so first we estimate the area in question. Okay, so here's the area we're looking at. Let's get rid of the cross-hatching for now. So what you're going to do is you're going to take the interval from A to B and cut it up into subintervals. Okay, just like we usually did. So now let delta x equal b minus a over n, and xi equals a plus I delta x. So that this is a, but it's also x0, x1, x2, x3, x4, x5, we're going to put the x5, and this will be x6 down here, which is going to be equal to b. All right. And now let's think of some rectangles. So later on, it isn't always going to be rectangles, but for now, it's rectangles again, like before. So this rectangle the area of this rectangle plus, it's just not nice looking there. I have a steady hand. There we go. The area of this rectangle plus the area of this rectangle plus the area of this rectangle. Area of this rectangle. And then this rectangle. and the area of this rectangle. All right, so the area of these rectangles estimates the area between the curve. Yes? So the area of the areas of these rectangles estimates the area between F and G. Right? I mean, just looking at that, we see that that's a decent estimate. And of course, you know, like before, the more rectangles and the skinnier those rectangles are, the better the estimate's going to be. Okay? But before that, so the area of this rectangle so here's a rectangle. Okay, what is the area here? Well, what are this point and this point? The point on the right, this point on the right, I should do it in red, I guess, huh? This point right here, this is f of x6. Or no, sorry, g of x6. This is g of x6. And on the bottom here, this is f of x6. Right, so the distance from here to here is g minus f. The distance between 2 points on a straight line is you know, is just the difference, right? So this is 5, this is -2. So the distance between them is 5 minus -2 is 7, right? So here, the distance from here to here is just g minus f, top minus bottom. Right, so this point up here, let's do it in red. This point here is y equal g of x on the top, xi. This point on the bottom is y equal to f of xi. Right, and the width of this rectangle was what? Well, it was just delta x. Right, so the area of this rectangle is the height times the width. Right, the height is gxi minus fxi times the width delta x. Right, the height of that rectangle is equal to the area of this rectangle is height times width, which is g minus f times the width delta x. All right, so the sum of the areas of all the rectangles is, well, it's the sum. I equals 1 to n gxi minus fxi delta x. So that's the Riemann sum. The estimation with rectangles of the area gets better and better as n goes to infinity. Thus, therefore, the area between fx and gx is equal to the limit as n goes to infinity. Sum I equals 1 to n. gxi top curve minus fxi bottom curve delta x. So we have that the area is equal to the limit of the sum of a function, don't care what that function is, function fxi, well it's not f in this case, it's like hxi, right? It's the limit as the limit of the sum, I goes from 1 to n, of a function hxi times delta x. The limit of the sum, the limit as n goes to infinity of the sum from 1 to n of hxi, just some function of xi times delta x. By definition, this is the integral. Not by any reasoning, that is the definition of the integral. That's the only reasoning, which, by definition, is the integral, the skinny sum, from a to b of the top curve, gx, the bottom curve, fx, I should turn that off, sorry, dx. Okay, so you see how we're using the definition of an integral to apply Riemann's sum to a not that different a situation that we had before, but it is a different situation to what the ordinary setup for the integral is. So throughout chapter 2, we're going to have other, other pretty neat definitions as well. This is the best. This is the best part of learning integration in your basic calculus classes, are these applications. This is the most worthwhile part, I think. So, to get like a real nice experience in the class, understanding chapter 2 is what you want to shoot for. All right, so example. So that's the theoretical talk right there. Now we just go through a bunch of examples. Okay. There we go. So find the area enclosed by the parabola y equals x squared and the line y equals x plus 6. All right, so the parabola y equals x squared, that's that standard parabola there that we're used to. And y equals x plus 6 is this line. All right, and we're looking to find this area in between here. Okay. Sorry about the phone. All right. Sorry. Okay, we're back. So the top curve is the line, y equals x plus 6, and the bottom curve is the parabola, y equals x squared. The only thing we need to know is what are a and b. All right, so a is right here, and b is right there. And how are we going to find that? Well, that's when x squared is equal to x plus 6. All right, to find a and b, all right, you just look at when the parabola meets the line. That is, when their y coordinates are the same. When x squared is equal to y, and y is equal to x plus 6. So we got x squared minus x minus 6 is 0, x minus 3, x plus 2 is 0. So x is equal to minus 2 or 3. So this is 3. This is minus 2. So the area that we're looking for here is the integral from minus 2 to 3, top minus bottom. Top curve minus the bottom curve. Okay, the greater minus the smaller. The greater is the one on top, and the smaller is the one on the bottom. So this is the integral from minus 2 to 3, so it's just a polynomial. I'll just do the antiderivative. So 6x minus 1/2, or no, plus 1/2 x squared minus 1/3 x to the third. From minus 2 to 3. So we've got, see, at 3 we've got 18. Yeah. 18 plus 9/2 minus 9 minus, at negative 2, it's minus 12 plus 2 plus 8/3. Right? So we've got 18 plus 12 is 20, minus 9/2. Let's see, plus minus 12, so minus 10. It's actually 28. Not 20, it was 28, right? 20, 30 minus 2, 28. Minus 9/2, and then minus 8/3. So a common denominator is, do that on the calculator here. So 28 minus 4.5 plus 8/3. 28 minus 4.5 plus 8/3. So 26. No, minus 8/3. 28 minus 4.5 minus 8/3. Yeah, 20.833. Okay, so that's the area between those two curves. Let's look at another one. How about this? So find the area shown. So I've got this curve, so this is y equals x squared minus 2x. And along with that, we'll have the line y equals x. So this is y equals x squared minus 2x. This is the line y equals x. And to that, we'll add the line y equals 2 minus x. And we're looking to find this area inside here. Okay? Well, I mean, we need to find, various interesting points here. All right, well, certainly this is the origin, 0, x equal to 0, right? What about this point here? This is where y equals x minus 2x is 0. So x squared minus 2x is equal to 0, which is also this point. Right? You just factor that. So x is equal to 0 and positive 2. So this is positive 2 right here. But also we need to know what this point is. Right? And then that point is where the line y equals x meets the line y equals 2 minus x. All right, so let's do that calculation over here. So x is equal to 2 minus x. So that's saying 2x is equal to 2, so x is equal to 1. So this line right here is the line x equals 1. So what we've done is we've split this area into two. And notice the top curve and the bottom curve changes at x equal to 1. Right? Here the top curve is the line y equals x. The bottom curve is x squared minus 2x. Here the top curve is y equals 2 minus x. And the bottom curve is x squared minus 2x. Right? So the area is split into two separate parts. So this is area 1, right there. Put that in a different color. So we got area 1 right there, and we've got area 2 right here. Okay, so total area equals area 1 plus area 2. Area 1 is the integral from 0 to 1. Top curve minus bottom curve. Top curve is y equals x minus the bottom curve, x squared minus 2x. By the way, make sure you put your parentheses where needed. Top curve minus the bottom curve. So minus the whole thing. So you got to put parentheses around that if it's got separate terms. Plus the integral from 1 to 2, top curve, 2 minus x minus the bottom curve, same thing. Okay? So this is the integral from 0, well, we'll just do the antiderivative. Let's write it out. So I got x plus 2x, so 3x minus x squared, plus the integral from 1 to 2, so 2, or 3x minus x squared. 2 minus x plus 2x plus x minus x squared, right? 2 minus x plus 2x is plus x minus x squared. All right. Antiderivative, 3 halves x squared minus 1/3 x to the third from 0 to 1 plus 2x plus 1/2 x squared minus 1/3 x to the third from 1 to 2. So this is 3 halves minus 1/3. This one is 4 plus 2 minus 8/3 minus 2 plus 1/2 minus 1/3. So you've got some big number here. So what's the common denominator for all this? I guess would be 6, right? So 9 minus 2 over 6 plus, so this is 36 over 6 minus 16 over 6 minus 12 over 6 minus 3 over 6 plus 2 over 6. Did we get that right? 9 minus 2, 6 minus 2, well, that's 36 over 6. This is 12 over 6. Minus 16 over 6 for the 8/3. Minus 3 over 6 for the half. And then plus 2 over 6 for the third. So what do we have here? 36. So that's 18 minus 21. All right, 36 minus 21. The minuses are minus 16 minus 12 is 28 minus 31. Sorry. Minus 31. The pluses are 38 plus 7, 45. So that's 16 over 6, which is 8/3. Okay? So that area is 8/3. And it's coming out positive like it should. Okay? It will always be positive, the answer for that. These types of area questions. Okay, one more example. How much time we got here? Last example. Find the area shown. So here is the curve. So now we've changed coordinates. X equals y squared minus 2y. And x equals y minus y squared. So we would like to find the area here. Okay. So first of all, notice we have functions x in terms of a function of y. Okay, so this time the area, so the area is always top curve minus bottom curve, but if you think of it as greater curve minus the lesser curve, you know, which curve has greater numerical area and which curve has lesser numerical area. Well, the x values to the right, right, these x values to the right are greater than the x values to the left, right? Minus 2, minus 3. Right? The direction of increase for x is this way, so the greater things are to the right. The direction of increase for y is that way, so the greater things are up top. Right, so here the area is equal to the integral from a to b, and a and b are going to be these points here. So this is going to be a, and then this is going to be b right here. Let me get rid of that. The integral from a to b, right minus left, dy. Right minus left, so greater minus smaller, to make it positive, right? Greater minus smaller makes this a positive quantity. So in the case of measuring things in functions of x in terms of y, it's right minus left. For functions of y in terms of x, it's top minus bottom. All right, and we just need to know what this point is right here, and that's where the two curves become equal. So we got y squared minus 2y is equal to y minus y squared. So this gives me 2y squared minus y equals 0. So I have 2y minus 1 times y is equal to 0. So y is equal to 0. That's that point right here. Or y is equal to a half. And that's, yeah, half. I guess the way I drew it didn't quite work out nicely. So this is 1/2 and this is 0. Did I do that right? Y squared, no, y squared minus 3y. Yeah, y squared minus 3y. So 2y minus 3. So it's 3/2. Right? So the area is the integral from 0 to 3/2. Now it looks better, right? Because that's 2 right there. Right minus left. So the right is y squared minus 2y minus the left, y minus y squared dy. So this is the integral from 0 to 3/2. 2y squared minus 3y dy. So this is 2/3 y to the third minus 3/2 y squared from 0 to 3/2. So we just evaluated 3/2. So it's 2/3 times 3/2 to the third minus 3/2 times 3/2 squared. So that is 3/2 squared minus 3/2 to the third. Oh, I have them backwards. The right is the y minus y squared. And the left is y squared minus 2y. Let's take another look at that. So the right is this one right here. I just have it written on the left. The right is this one right here. right, which is the y minus y squared. And the left one for the region is this one here, which is the y squared minus 2y. So what it does is it negates this. So it's 3y minus 2y squared. So antiderivatives, 3/2 y squared minus 2/3 y to the third. So 3/2 squared, 2/3. So this is cubed minus squared. So that's 27 over 8 minus 9 over 4. So that's 27 minus 18 over 8. So 9/8. Okay. All right, so that's it for this section. I will see you later.